Our speaker is Apo, and he'll be talking about independent component analysis. And this will be for 1 hour 45 minutes before we go.
Okay, hello everybody. So basically my fundamental goal is to talk about independent component analysis, but to begin with I will first use some slides stolen from my co-author Jarmo Hurri to talk about some kind of background on things like principal component analysis, which is often confused with ICA and other kinds of stuff. So this is the contents of this introductory part, which takes something like 1 hour, 2 hours. Actually, I have no idea. Perhaps depending also on your questions, you may interrupt me at any time and ask, because, well, I suppose it is, I don't know very well what is your level of background knowledge on these subjects. I suppose it is also quite variable. So first I will show some basic ICA examples. So what is ICA all about? And then I will go into this kind of stuff like multivariate optimization and especially multivariate statistics and estimation theory that are the necessary theoretical background. So here's a very nice illustration, and probably I think also a very impressive illustration of what ICA does. So here what we have, originally we had 6 images that you will see in a while, but here what we see is only linear mixtures of those images. So I mean these grayscale images have simply been linearly mixed by adding the grayscale values together with some certain random coefficients that we don't know. Now the point is that, is it possible to find the original images without knowing the coefficients of that mixing? So that is, the only data that we have is this thing here. So 6 mixed images and nothing else at all. So can we find the original images? Well, you may, as you may guess, with ICA we can. When you do ICA, you compute the independent components. So ICA means independent component analysis. What you get is these 6 original images, which some of them may look a bit weird. That's because they have been inverted. I mean, the polarity has been inverted. Black and white have been inverted. But still, if you can invert them back, and then, well, you will see that actually, yes, you did get all of those 6 original images. So in terms of statistical estimation, what we have here is latent variables model, and these independent components are latent variables. Latent meaning hidden. We will have something about that a bit later on. And so this mixing was completely linear. ICA, as I will consider here, is a completely linear method in the sense of having a completely linear mixing. And here's another example, well, a bit more practical example, because you may not encounter that kind of linear mixings of images every day. But this is really a practical example where we have recorded brain activity, electrical or electromagnetic brain activity, using a sensor that has, a large number of sensors, basically something like 100 or 200 sensors that are located on just outside of the head. And so here basically these 3 last ones are just for reference. I mean, they are not really recorded. They are not really of interest here. But the point is that all these signals here are given some of the outputs of these sensors. And what you can see is that there's some kind of a some kind of a mixing of certain kinds of phenomena. You see that like this kind of stuff here occurs in many different sensors. But well, intuitively, you would think that there's kind of these signals are a mixture of a lot of different kinds of interesting original signals. A laser pointer, you mean? Yeah. This thing, okay. Oh. But this is also very nice. Kind of a phallic symbol. So. So this is a real practical application of ICA. People have done this kind of stuff for a couple of years, and here's an example of what you might get. Here are some 9 independent components that have been estimated from that, and if you analyze them further, you will see that there are actually some of the independent components correspond to something like really independent sources of activity. Well, not necessarily in the brain. Some of these correspond to, for example, heartbeat and so on. Well, but in any case, ICA will find some kind of underlying sources of activity in these brain signals. We will have more about this towards the end of these lectures. So, ICA has found application in many different application areas recently. Here's a rather arbitrary list of those. Well, most probably the most prominent and most successful application has been in analyzing this kind of biomedical signals in techniques called EEG or MEG, which are about measurement of brain activity, and MRI and fMRI, which are measurements of, well, also partly about brain activity, or then something like about brain anatomy. But also you can do, it's not necessarily, it doesn't need to be related to the brain. You can measure, for example, electrical activity of the heart and that kind of stuff. And their ICA seems to be successful. Then, well, my own specialty is mainly in computational neuroscience, where the idea is that we try to model some kind of a sensory processing in the brain. The idea is that the brain processes sensory information in a statistically highly sophisticated way, and it happens that this sophisticated way is very, very similar to independent component analysis. Then another application that's certainly growing in importance recently is bioinformatics, especially transcriptome analysis or gene expression analysis. I suppose we will have talks on that here. So far there has been only a couple of papers published on this application, but I think that will become very important in the future. And there's, well, my co-author then has written some rather arbitrarily some further applications. Telecommunications is, of course, also one very big area for this kind of techniques. So now we will start. I will start looking at some background knowledge. Well, first I'm going to talk about optimization. Of course, optimization is a very complex issue, and Nick will give us a lot of details on how to optimize multivariate functions. So here we have just two slides on optimization, one of the shortest courses on optimization that you could imagine. So, well, of course, the very point is that we have a function of many variables. We are maximizing in a multidimensional space. If you are maximizing in a one-dimensional space, things are rather trivial. You can, well, basically you could just plot the function and see where the maximum is. And, well, you can also numerically find it rather easily. But when we have a multidimensional space, let's say 100, 1,000 dimensions, then things get very complicated. The fundamental basis for almost all these methods is to use the derivative or the gradient. Well, the gradient is basically the vector given by the different derivatives. The idea is that since the derivative gives a local linear approximation of the change in that function, well, then we can use that approximation and go to the direction where this approximation grows as fast as possible or decreases as fast as possible if you want to minimize the function. So, well, basic differential calculus will tell us that the change when you add a small delta W to the argument, I mean, when you move just a little bit in that space, the change will be proportional to the. Actually, it will be equivalent to the dot product of the derivative or the gradient times the change. So then it is obvious that to kind of go in the best direction, you should actually go in the direction of this gradient, because then this dot product will be positive and as large as possible. And so that gives rise to the gradient rule, which simply says that when you are in a certain point and you want to find a point, when you want to find a point where this function is bigger, then you just add the gradient multiplied by a very small constant. Plus or minus here means, well, it depends on whether you want to maximize or minimize your function. Then things are a bit complicated in practice for various reasons. One is that you usually have some kind of a constraints. You don't want to maximize over all possible values in this n-dimensional space, but you have some kind of constraints. For example, let's say that you want to maximize on the unit sphere, you say that the norm of W should be equal to 1, something like that. In general, you usually express it as some kind of as an equation where you have some function of W equal to 0. So then the so-called Karush-Kuhn-Tucker conditions tell you, or KKT conditions tell you that in an optimal point, what you should have is that the gradient of this function to maximized is proportional to the gradient of this constraint. In other words, gradient plus some constant times the gradient of the constraint equals 0. And well, yes, this is really, just giving the basic ideas, but then you can, based on these ideas, you can then develop different kinds of iterative methods, which are, well, the basic methods are kind of slight variants of this, of the gradient method. For example, projective gradient is simply based on the idea that you kind of go into the direction of the gradient, but still you kind of always project the change onto this constraint surface, on the surface where h of W equals 0. Okay, that was a rather short course on optimization theory. But that's something that I suppose we always need in machine learning kinds of stuff. Then the question is that what kind of functions are you actually going to optimize? Where do you get your objective functions? Well, in ICA, we get them basically always using from principles of statistical estimation theory. And that's what I'm going to talk about next. So I'm going to first after some basic notations and very basic concept, I will talk about especially about the multivariate Gaussian or normal density, which is like the fundamental density in n-dimensional spaces. So we are all the time here talking about multivariate statistics. So I'm not going to give you examples of univariate densities like exponential densities or Laplace densities or what other people have been talking about. This is all about multivariate statistics, which is again, of course, much more complicated than one-dimensional statistical modeling. And then I will talk about principal component analysis, which is some kind of an ancestor of independent component analysis, and then of the very important principle of statistical independence. Because when we talk about independent component analysis, it is not perhaps, it shouldn't be very surprising that statistical independence will be very important. So just some basic notation. So we have random variables. Random variables are variables who take random values or something like that. Well, there are, I think, somewhat more rigorous definitions available, but I seem to forget them. So random variables, the distribution of a random variable is often described by a density function. Well, in the this is possible in the case where we have random variables which take like all kinds of values on the real axis, for example. We are not going to talk about anything that takes discrete values in this lecture. So we are never going to have something like the probability that a random variable equals 0 or that it equals 1. Everything is always continuous valued, and actually in basically all cases these random variables can take all values on the real axis. And so then in that case we can express the probability distribution function using the density function. And then in particular we will be talking about random vectors, which means simply that we have a large number of random variables. So it's like kind of you could say call it a multidimensional random variable, but usually random variables only are the word variable here is restricted to one-dimensional variables only. And yes, again, you can then express the distribution of continuous valued random variables using a probability distribution function. Well, here my co-author gives shows how the distribution, how the density function is related to the cumulative distribution function, which is, well, a well-known stuff in basic probability theory, but, well, let's not go into that. Yeah. Okay. So, well, after this stuff, these things like densities and so on, certainly the most fundamental thing in probability theory and statistics is the expectation. Expectation is in the basic case, we talk about the mean, which is the expectation of a random vector itself. And there are different kinds of terminologies available, but then people often talk about expectation when they talk about some kind of the expectation of some function of this variable of this random vector. So the expectations are computed basically by an integral where you have, well, first this function of x and then multiplied by the probability density function, and then, well, that's integrated over the n-dimensional space. And so the most interesting expectations in addition to mean are the correlations. Well, perhaps I shouldn't say most interesting ones, but let's say the most basic ones. Actually, in IC, one of the points in ICA is that these correlations are just like the first step in analyzing random variables or random vectors, and you should not be content with just using the correlations. So, I should perhaps here explain what is actually the meaning of correlations. Well, correlations are basically tell you something about linear dependencies of these variables. So let us say that we want to predict x2 by x1. So this is classically expressed as a linear regression model that I'm sure you have all seen somewhere. We have a coefficient a here, and then we have some kind of a noise or residual term which is random. So another point is that a tells us, well, gives us what is loosely called the correlation between x1 and x2. Well, if it's positive and large in some sense, then it tells you that's when x2 in a certain way follows x1. So that when x1 is large, this one will be large, and when x1 is small, this one will be typically large. Now it turns out that if we normalize these variables properly, then we will see, actually, if we normalize them so that the variances of x1 and x2 are both equal to 1. And well, just for those of you who don't remember, I will remind you of the definition of variance, which is a measure of the spread of the random variable. So now what happens is that under these conditions, this A equals the correlation. It equals expectation of x1 times x2. So this correlation tells you something about the dependencies between the variables. But also it is important to note, in the context of ICA, it's important to note that correlation only tells you the dependence in the framework of this kind of a linear dependency. So correlation is really like the first step in the direction of analyzing the dependencies between these vectors. For example, if you wanted to know how the square of x2 is related to the square of x1, then you wouldn't be able to use this correlation anymore. You would need something completely different. Well, actually, something like the correlation of the squares. Then. Yeah. So I should also warn you that the terminology here is very confusing in the sense that, well, this definition of correlation is what people usually use in signal processing. In statistics, when they talk about correlation, they usually use the word correlation coefficient. And correlation coefficient is a different thing from correlation in this sense. It is actually a normalized version of this. No, not a normalized version. It's really it's a rather different. It's not a very different thing either. It's kind of the same thing, but it has slightly different constraints. Actually, we will see something about that on the next slide. So, in addition to covariance, the correlation matrix, people talk about the covariance matrix, which is done so that basically you subtract the mean of each of the variables, and then you compute the correlation matrix. So, which means that if the mean is 0, then actually the covariance matrix is just the same thing as the correlation matrix. Now, what is not mentioned here is a definition of the correlation coefficient, which is the same thing as the covariance divided by the variances. The standard deviations of these variables. So it's kind of the correlation coefficient is a renormalized version of covariance. And now there's actually something even more confusing. Yes.
The first matrix. Would another word for that be the second moment matrix?
Yes, the second moment matrix. Yes, exactly. Now maybe I shouldn't, confuse you with this, but I have to. Now, a very widespread terminology is to say that if the covariance is 0, then these variables are called uncorrelated. So uncorrelated does not mean that correlation is 0, which would be very too logical, I think. So uncorrelated means that the covariance is 0. Well, fortunately, during all these lectures and in many other contexts as well, the expectations are all 0. I mean, the expectations, the means of the variables are all 0. So then uncorrelatedness is the same thing as 0 covariance, which is the same as 0 correlation. But in some cases, there will be some differences. And in that case also it is the same as having a 0 correlation coefficient. Okay. Yes. Okay, that's it. Oh, yes, I'm sorry. Here I made a mistake. So again, here, this thing here, this should actually be the covariance. So actually, let's make here the assumption that the expectations are 0. Only then this thing here is correct. And that's why people talk about. Then it's easy to talk about correlation. In all kinds of sciences, social sciences and biological sciences, people always talk about variables being correlated. Now, then for them it is usually a question of having a non-zero correlation coefficient. Now, if this condition, having a non-zero correlation coefficient is then the same thing as having a non-zero covariance, which means then a non-zero A, which means that you can like linearly predict one variable by the other one. Or I mean, you can predict part of the variable by the other variable. People often talk about like percentage of variance, which is predicted, so that if there's like a weak correlation, then you can perhaps predict 10% of the variance of the other variable. If the correlation is extremely good, then you can perhaps you can predict maybe 90% of the variance and so on. If the variables are uncorrelated, then you can predict 0% of the variance. Okay. So here's a classical example. We have here a certain number of people, and we have their weights in kilograms and their heights in centimeters. And you can then compute the covariance matrix. So in the covariance matrix, actually the diagonal elements are nothing but the variances. And it is the off-diagonal elements that give the covariances and tell you about the dependencies between the variables. So what you see here is that there is a rather substantial dependency, a rather substantial correlation between the heights and weights of the persons, which is not at all surprising, of course. This is seen in the fact that the covariance is larger than 0. Another thing that you can see is that you can also compare the variances if you like. Well, that is perhaps not so interesting. What people usually use to model this kind of data, also this kind of a data. I mean, this is kind of a very typical kind of a cloud, as some people would call it a Gaussian cloud, because it's kind of a elliptical cloud. It is very often, well, almost always modeled by this kind of a Gaussian densities. So this is a contour plot of a Gaussian, multivariate Gaussian density, where the parameters have been chosen so that it's kind of slightly similar to this real example. So these are just two representations of the same distribution. So what you will see is that the contours are elliptical. That's always true for Gaussian multivariate Gaussian densities. So it will give you, if you take a sample from this thing, you will typically get a cloud that looks something like elliptical, and then there's some points which are a bit further away from the center. And well, yeah, here's just the same thing presented in a different way. And well, the mathematical expression for that kind of a density is given here. So the probability density function of x is some constant, normalizing constant, times the exponential of a certain kind of a quadratic form. So here we subtract from x its mean, actually. Mx, it's a parameter which turns out to be equal to the mean, and then we take a quadratic form multiplying by this x minus mean a certain matrix from both sides. Now it turns out that this matrix here is the inverse of the covariance matrix. So we see that this is like one of the simplest. Just looking at it algebraically, you will see that this is one of the simplest imaginable densities that you can imagine in an n-dimensional real space. What you see is that, first of all, these parameters, it has two parameters. One is the mean, which basically tells you like where the center point here is, and then we have the other matrix is the covariance that basically tells you like what is the shape of these ellipses, what direction they are pointing at, and how big they are, and that kind of things. And well, usually in statistics, what is more interesting than the densities themselves is the logarithms, for reasons that will become clear in a moment. So what we are having here, so the logarithm of this probability density function is simply a quadratic form. And well, the quadratic form is one of the simplest functions possible. Of course, a linear function would be even simpler, but we cannot have a linear function as the logarithm of a density function. A question, why cannot we have a linear function as the PDF probability density function? Sorry? Yes, exactly. It has to integrate to 1, and a linear function would go to infinity in some of the directions. Yeah, and so yeah, here the meaning of this constant k is to make sure that this probability density function integrates to 1. It has a slightly ugly looking expression, but still it can be computed rather easily. So another point to note, well, about the Gaussian distribution is that once you know the first and second order statistics, that means the mean and the covariance matrix, then you have completely specified the probability distribution function. You don't need any other information, and any other information will not bring anything new about the distribution. Okay. Do you have any questions at this point? Is this too trivial? Is this too difficult? No. So, the classic way to approach when you have data from a multidimensional and n-dimensional distribution. The classic way to analyze, one of the simplest ways, is to do principal component analysis. Well, you can do things like cluster analysis, for example, but, well, for data clouds like this, you will see that, well, cluster analysis is not very interesting because there's basically just one cluster. So what you can do, what people do is principal component analysis, which is closely related to the fact and to the fact that people use a Gaussian model for modeling this kind of data. The mathematics are very, very similar. The mathematics and the underlying assumptions are very similar. So well, I think there will be some talks here where principal component analysis is described in much detail, but I have to talk about it for a while, because otherwise you wouldn't be able to understand the contrast to independent component analysis and what is very new, what is really different in independent component analysis. So usually principal component analysis is defined in a recursive manner. Well, there are a couple of different ways, but let's start with the recursive manner. That is, we want to find a single principal component. A single principal component means a single direction in the data space which is given by a single vector in that data space, which we denote by W. So now the point is that we approximate the data using the projection of the data onto this single principal component. Well, the projection, assuming that we normalize W so that its norm is equal to 1, the projection of the data the projection of a single data point onto this one-dimensional subspace on this one line in this n-dimensional space is given by this expression here. Now the question is, what is the best W? Yeah, well, the question is, what is the best W? Well, there are certainly many different answers on what is the best W. You have to first define what is best. Well, the way best is usually defined here is that what is the best W so that you approximate your data in the as well as possible. Approximation means that now the expected error or the average error between the real data and this projected approximated data is as small as possible. Yeah, so now we have a typical optimization problem. We want to minimize this function, which is the approximation error, expectation meaning average over the whole data set, whole data distribution, and we have, this is a constraint optimization problem because we say that W has unit norm. So the derivation on how to do this is given here. So this was written by my co-author, so I'm not quite sure if I understand it correctly myself. But so let's try to go through it. Maybe we can learn it. So the point is that first we define, we make a change of variables basically. Instead of considering the variable W, we look at the orthogonal direction. Well, it's simple here, especially because we have only two dimensions. So once we define the dimension of W, we have uniquely defined the orthogonal direction. And so now we transform this objective function. How is this transformed? Yes. Oh, yes. We express x. Sorry. So yes, we express x as the sum of the projections onto W and U, because, well, that is equal to x because we only have two dimensions and we have two orthogonal projections, and then the approximation is just as given by the definition. And so then these two terms cancel out, and what we have is this kind of a thing. Now, when you just express this norm, well, norm of a vector is, the square of the norm of a vector is simply the transpose of the vector times the vector itself. So here we have the transpose of the vector and the vector itself. Now the point is that well, first of all, well, here we change the value, change the order of these things. I wonder if this is quite correct. Well, Yeah, it
Yeah, it's okay.
is it okay? Yeah. So now we commute these two terms here, and then we take the expectation operator here into the middle. We can do that because u is a constant and not a random quantity. So then what we get is the expectation of x transpose here in the middle, and yes, I don't quite get it, but I have to trust my co-author that it's correct. Or do you think there's an error here?
That U transpose X is a scalar, so you could actually write it as U transpose X all transposed. And then if you expand that, the U's cancel out.
Yes, some of the U's cancel out, but I somehow get the impression that
Then you take one from the right back.
Okay, yes, yeah. So it has to go somewhat. So that this thing here is equal to x times ut times utx, and then we commute those xt times u, and then this thing will be multiplied by u. Right, yes. So now these things here cancel each other. So because this is a scalar, so we can actually put this here, and because the norm of u is equal to 1, then these things cancel each other. And what we can put the expectation operator here in the middle. Can you see this? And it's equal to this. Yes. And so now what the expectation thing here is nothing but the correlation matrix. So we see here two things. First of all, principal component analysis basically boils down to looking at the correlation matrix, or the covariance matrix. Usually these are all zero mean variables. And the second thing is that it boils down to something like analysis of some kind of a quadratic forms. Well, the next slide is then how to maximize this kind of a, actually here we want to minimize this quadratic form. Now again, let's try to understand this. So what we want to minimize this kind of a quadratic form under the constraint that the norm is equal to 1. Now when we the gradient of this thing, so well this is the condition. Sorry, I said you Karush Kuhn Tuke conditions, but actually I think that's kind of an exaggeration, because those are the more general conditions that are used with inequality constraints. So this is just the classical Lagrange condition. So we will have that the gradient is proportional, or I mean gradient minus some constant times the gradient of the constraint equals 0. And now it happens that the gradient, well, okay, here my co-author uses not the gradient but the transpose of the gradient, which is more properly speaking the derivative, but it doesn't make any difference really. So here the derivative is equal to is the corresponding linear function. This is an interesting point, that the gradient of a quadratic form is the corresponding linear function with the same matrix multiplied by 2. And then here, well, we have the same thing, because this is also a quadratic form with an identity matrix in the middle. So these equations, when we just take the 2's out and put this u on the other side, it gives you this. And this is nothing but the definition of an eigenvalue of a matrix. So this is actually a very general phenomenon. Usually when we have some kind of a quadratic functions, quadratic forms to maximize, the solutions will be given by some kind of eigenvalues, because you always get the same kind of equations. And here, well, then it depends on depending on the situation, you have different eigenvalues that you want. Sometimes you have the largest eigenvalues, sometimes the smallest eigenvalues, sometimes something in the middle. So what happens here is that we should actually find the largest eigenvalue sorry, in this case for U should correspond to the smallest eigenvalue of the correlation matrix, which is a bit confusing. Actually, W, what we actually wanted to find in the first place, which was the original variable, corresponds to the largest eigenvalue. Well, whatever. The point is that we can do PCA by taking the correlation matrix and then computing the eigenvalues. And this the eigenvector with the largest eigenvalue will give us this principal component. And now, as I said in the beginning, PCA is basically a recursive thing. So now we have just shown how to compute one principal component. But in an n-dimensional space, you can define n principal components. So the following ones are defined simply so that we subtract this projection that we had in the first place from the data. So we reduce the dimension of the data by 1 and then do exactly the same thing. So what we are doing is that we are, well, in this two-dimensional case, it is not very obvious, but in an n-dimensional case, we are successively computing components that give us the best approximation of the data using this limited number of components. Actually, it can be proven that the first k principal components give the best approximation of the data that is possible with a k-dimensional subspace.
Actually, you get quite a different answer if you change the units.
Sorry?
If you measure pi to the meter, you get a different answer.
Yes.
It's not very sensible.
Yes, it is. One problem with PCA is that the result depends on the units of measurement. So,
You not only use the correlation matrix. Correlation matrix is there to make it scale invariant.
yes, again, so now you are talking about the matrix correlation coefficients as defined in statistics. Yes, so correlation coefficient as defined here and in signal processing does have the same problem of depending on the scale, that it depends on the scale. But yes, the classical way of getting rid of this problem is to simply define the scale of your variable so that you say that the variance of each variable has to be equal to 1. But yes, I mean that kind of solves the problem, but then I mean it gives you a unique answer to the problem, but it may not be the answer to the question that you wanted to ask in the first place, because in some cases the units have an intrinsic meaning and you don't want to rescale everything. Yeah, but it depends on the situation. Yes, but so as I said, the k-first principal components give the best approximation of the data, in the sense that when you project the data onto the subspace defined by those principal components, the expected square error will be minimized. So that is why PCA is used for dimensionality reduction. So if you have data that has like 10,000 dimensions, for example, and let's say that that you want to use some computationally intensive methods that cannot really cope with 10,000 dimensions, and you need to reduce the dimension of the data to be able to use your favorite method, then a PCA is the classical way of reducing the dimension. Now, with PCA you can reduce the dimension to say 100, and you know that you have the best possible approximation of the original data, the best possible with 100 dimensions. Though, of course, this is, well, best is always extremely relative. People always prove some kind of optimality results for different kinds of methods, but of course what is optimality is always in the eye of the beholder, I suppose one would say. So we must remember that like PCA here, as defined here, has, for example, the constraint that it is completely a linear method. So then some people have, well, actually many people have been developing methods for nonlinear dimension reduction, which are something like nonlinear PCA methods. There are methods called, for example, non-metric multidimensional scaling, which is like the oldest group of methods. Then there's self-organizing maps, curvilinear component analysis, kernel PCA and like isomap or local linear embedding, which was developed by Sam, so it is certainly the very best one available, and so on. And of course, you could also question the very objective of this very measure of what is the best approximation. So what we are talking about here is the approximation with respect to the Euclidean norm. But of course, you might argue that perhaps some other kind of a measure might be better under some circumstances. But in any case, the nice thing about PCA is that it is computationally extremely simple, because we can just do the eigenvalue decomposition of the covariance matrix, and that's extremely simple compared to all other all these nonlinear methods, and also compared to ICA and so on. In signal processing, people also talk about noise attenuation as a great benefit of PCA. There the idea is that like you have a signal that lives in some kind of a low-dimensional subspace called the signal subspace, and then you have noise all over, like noise in all other directions, not which are orthogonal to this signal subspace. So when you get rid of all those noise dimensions and just concentrate on the signal subspace, then you probably get rid of a lot of noise as well. Well, that may be true or not, depending on circumstances. But really, the good thing about PCA is dimensionality reduction, and I would say that that is really the only thing where we know that PCA is really good. Like, the point is that people have trying to use PCA for things that actually ICA does properly, but which PCA does not do properly at all. That PCA completely fails to do at all. So we have to. So we will see that PCA is good for dimensionality reduction and not for many other things. So here's a classical example of this dimensional reduction property. So here we have an image. This is an image that we want to now compress. Compression means here that we divide the image into small squares, small windows, and then we project all of those windows onto a lower dimensional subspace. But this is not very different from methods used in well-known image compression methods as in JPEG, for example. They don't use PCA, but they use this idea of looking at small windows and dimension reduction. So if you take this kind of a small windows and then and sample the image and get all possible windows, non-overlapping windows, then you can compute the PCA for that kind of a data, and what you get is this kind of a basis vectors. These basis vectors are rather similar to something like Fourier basis vectors, or partly similar, partly not. At least these first ones are something like not very different from Fourier basis vectors. Now the point is that we can have different kinds of compression, which means that by ignoring a certain number, a certain percentage of the vectors. So now here, in this case, what we have done is to ignore 90% of the principal components, and we have only taken the 10 first. That is the 10 most important principal components. So we have basically, in a certain way, you could roughly say that we have reduced the amount of data by 90%. But as you can see, it's not terribly different from the original image. You can see some kind of a smoothing, but not too much. So if you take more and more principal components, here we have 25%, and here we have 50%, you will see that the picture gets better and better. Yes?
But when you say that this is used for compression, if you sent me these 10% of the coefficients, how would I reconstruct the image? Don't you also need to send me the basis?
Yes, I do. Yes. But of course, depending on circumstances, the basis, the amount of coding needed for the basis may be quite negligible compared to the the coefficients. Of course, this is also why people don't use PCA for real compression of images. They use the fixed basis sets. But I mean, the idea is that with PCA you could find some kind of a optimal basis for doing that. But I mean, you wouldn't compute the PCA separately for each image. You could, for example, if you have a certain class of images, you compute the PCA, and then then it doesn't take much storage. Yeah, here's the original one again. Okay, that was about PCA. Now, when we're talking about independent component analysis, we have to understand what is independence. And, well, there are different kinds of independence. This is about statistical independence. It should not be confused with linear independence, which is a completely different phenomenon then. So statistical independence basically means that when we have, let's say, two random variables, x and y, when we know the value of x, that doesn't give us any information about the distribution of y. Or in other words, no, x doesn't give us any information about y, to put it a bit short. So what this means, to formulate this mathematically, well, we use the concept of conditional distribution. I hope that's familiar to everybody. Well, yeah, it must be. I think Sam gave us a good introduction to that kind of stuff. Yeah, so we all know what is a conditional distribution. So this is a conditional distribution now for continuous valued variables. So it is a conditional probability density function. But it doesn't really make any difference whether we are talking about conditional probabilities for discrete variables or whether we are talking about conditional probabilities for discrete variables or conditional probability density functions for continuous valued variables. So the conditional probabilities of y given x is defined by the joint probability density divided by the probability density of x for these given values of x and y. So if we say that x doesn't give any information about y, then it means that the conditional distribution or the conditional density should be equal to the original density of y. Well, if you just now then take this equation and multiply by px of x and put it here, then what you see is that this is the same thing as saying that the joint distribution factorizes. That means the joint density is simply a product of the marginal densities of x and y. And yes, this lower equation here is the typical definition, well, the formal definition of independence. And as I talked about, when I talked about here about correlations, I was saying that, well, yes, correlations are about some kind of a dependency between random variables. But the point is that correlations only talk about one very particular form of dependencies. It is this linear dependency in the sense that when x1 is large, then x2 is large. When x1 is small, then x2 is small. But independence here is something much stronger. So statistical independence, so there are many different kinds of dependencies. So when we say that two variables are independent, it means that they have no kinds of dependencies there. So they don't have this kind of correlations, but they don't have any other kinds of dependencies either. So statistical independence actually implies that the covariance and the correlation coefficients are zero between those variables. But it is not true in the other way. Just being uncorrelated does not imply independence. We will talk more about that later when we actually get to the stuff on independent component analysis, if that ever happens. Okay, so maybe now we have a short break and then continue.